Okay, time for MDPs. Let me just throw up the schedule so you see where we are in the class. We are just about halfway through. So the class is these 5 chunks: combinatorial search, certain knowledge, planning, learning, uncertain knowledge, and we are right in the middle of planning. We're doing the last chunk of planning, which is on MDPs. That's where we are here. So, in fact, you're slightly more than halfway through because there are 28 class meetings, and this is number 16. So last Monday was, middle of last week was the halfway mark. So don't despair. It's going to end soon. All right, so let's talk about MDPs. MDPs. Okay. Markov decision processes. Whew. So a decision process is where you have to make a series of decisions. I call that planning. Like, what's the next action to do? What's the next action after that? What's the next action after that? You have to make a series of decisions. There's an area of study called random processes. So a decision process very often has a component of randomness and stochasticity. We're going to talk about decision processes that are Markov. This is this famous Russian guy, and he studied systems that turned out to be Markov, so everyone calls them Markov systems. And as we talked about several classes ago, a Markov system is a random system where the probabilities only depend on the current state of the system. So if I'm here and I do action A, I'm not quite sure what's going to happen. There's randomness in the world. Not everything is perfectly reliable. We've all had flights delayed. We've all had alarm clocks not go off. With some probability, I'm going to go to this state, maybe with probability 0.9. Maybe this is state 23 and this is state 47. So with probability 0.9, I go there. With probability 0.1, I go over to this other state. Maybe it's state 13. I don't know. So a single action can have multiple different outcomes. Now, there might be another action I can do. Action B. Maybe action B. Maybe action B takes me, with probability 0.45, takes me here. I don't know what state that is. State 7, maybe. And with the rest of the probability, it takes me up there. Probability 0.55. Now, what's Markov about this is that the probability of my ending up at 47 after doing B is independent of how I got to 23. All right, this is like maybe this is where Wheeler throws up, and this is where he eats like one more donut. And it doesn't depend how many donuts I've had that morning. Okay? Now, if that's important in modeling whatever system you're dealing with, and I can tell you it is for me, modeling my dietary response to donuts, it depends. If it depends how many donuts I've already had, then you need to make that part of the state. So state 23 becomes the state of, Wheeler has already had 7 donuts. I can eat 6 donuts, no problem. 7 donuts, things start getting iffy. I think I did eat like 8 or 9 donuts once.
Are we talking donuts or donuts?
Donuts. I love donuts, if you don't know. It's like, yeah, I love donuts. I have a weakness for donuts. I can't stop myself. Every time I go to a donut store, I buy a dozen donuts. Like, I'm not capable of going into a store and buying like one donut. That seems so pathetic. How could you just buy one donut? Have you been to the Stonehouse Bakery in Barrington? It's actually pretty good. Dunkin' Donuts are terrible, but the Stonehouse is actually pretty good. I was very happy when I discovered them. It's the only good thing I know about Barrington. Other than Mendham's Pond, I guess, which is nice. Okay, so does everyone understand the Markov property? Yeah? Evan? Yeah? Yeah? Okay, cool. Okay, so Markov decision process is where someone hands you one of these things. This is a Markov decision process. Is like, what do? You know, you're at state 23. How do you? What should you do? And so, well, this is most of a Markov decision process. There are going to be other states, and you know, there'll be other actions that'll take you various places, and you know, who knows how the state space is connected. Plus, luckily, it's not just a maze of decisions. There's actually reward as well. So good things can happen to you. When you transition into a state, gold falls from the sky. Or I puke. Yeah, that's the negative. There's positives and negatives. So it's all on the same scale, though. This is pretty disgusting. So, yeah, you get this is an MDP, there's an initial state, there's a transition function that says if I'm in S and I do A, what's the probability I'm going to end up in S prime? Then there's this reward function that says, hey, you got to that state, here's the reward. Some people phrase their MDPs in terms of costs. I like reward. I'm a more positive kind of guy. And then there's some MDPs have terminal states where you stop, like end of game, life over. So that's an MDP. Now, this word probability is probably going to be mentioned in like 0.9, with probability 0.9 in every class we have till the end of the semester. So up to now, we've been in a very discrete kind of world, and we've just been dealing with, you know, binary, yes, no, this is where what state you're going to go to, you're not going to go to that other state. Now everything's getting probabilistic, so they're going to be numbers. So brace yourself, okay? Some people like numbers, some people do not like numbers. A lot of computer scientists don't like numbers, because we do a lot of like discrete, logic-y kind of stuff, but there are numbers now. So brace yourselves. In particular, one of the kinds of numbers we're going to be using a lot these days are called probabilities. And my sense is that every UNH undergrad is required to take a class on probability and statistics, but a lot of times they come out of the class and they don't still really know that much about probability and statistics. So don't worry, we're all in this together. We're going to get it figured out. This is everything you need to know about probability. Yeah, you know, for each part of the class, there's one thing you have to know to do well. Like for the logic, it's implication goes into not A or B. For heuristic searches, it's F equals G plus H. For this part of the class, it's probably this definition of conditional probability. So we'll get there in just a second. We're going to work down the list. Probability. So I don't know that much about probability either, so the class is not going to get all that advanced. My understanding is that a random variable is something that you don't really know the value of. It could come out a bunch of different ways. And we're just going to be dealing with propositional random variables, so they don't have any special structure. They're just like X, a random variable X. Now, a random variable can have either a discrete or a continuous domain. So you could have a random variable X that stands for, like, it's going to be located inside or outside. Like, that could be discrete. There could be two possible values. We have a probability distribution over two possible values. Like, the coin's going to come up heads or tails. I think that's called a Bernoulli variable. It just has two values, true or false, or heads or tails. You can talk about the probability of it being heads. There are also random variables that are continuous, like what's the temperature going to be tomorrow? I don't know. Nobody knows. Random variable. We'll find out tomorrow. And for random variables like that, people like to draw probability distributions. So, like, I don't know what the temperature is going to be tomorrow. If here, I think it's supposed to be like 50, 40? I don't know. 40? Anyone know? Okay, well, let's pretend it's going to be 50 tomorrow. So we might have some information about what temperature it's going to be tomorrow. We might have a belief. Like, it's probably going to be 50 degrees. This is a probability distribution over the possible values of tomorrow's temperature. And sometimes life is just too complicated, and we only consider distributions that have certain shapes, like bell curves. Those are called Gaussian distributions. So here's a Gaussian centered at 50. So this is a random variable that has a continuous domain. So probabilities are random variables that have a continuous domain between 0 and 1. And the probability across all the different outcomes has to sum to 1. Right? Makes sense? Obviously, like, it can't, I'm going to flip the coin. It has a 0.7 chance of being heads and a 0.5 chance of being tails. Like, that just doesn't make any sense. So the sums to 1. Oh yeah, that probability distribution I just drew is also called a density, probability density. Like, it's densest around 50 degrees. And in order to be very general, like, so there's so many different kinds of variables and so many different kinds of distributions that they might have that people sometimes use a big fancy word called expectation instead of average. Instead of just saying the average value is blah, they'll say the expected value is blah. And average, like, if we talk about the average height in the room, it's like we take all the different heights and add them up and divide by the number of people. That's assuming that each of us counts the same. And as you know, some of us in this room count a little bit more than the others. So for that, you'd have to compute an expected height in the room, where I might get twice the weight of all of you. And so you take the probability that your random variable has a particular value and multiply it by the value. So you're weighting the value by the probability. So we talked about the expected value of x. It's this weighted average, if you want to think of it that way.
Does that work for continuous variables?
Yeah. I don't know any math, so don't hold me to whatever integral I might have written up there. But yeah, I think it does.
Yeah, it's an integral, not a sum, so that would apply for continuous space.
Yeah. So now the slides take the notation of your book, but your book's notation is kind of confusing. So just be aware. And I should really be redoing the slides as we go to make them even clearer. The probability that some variable x has the value x1 of all the different values it could take is often written as probability of x1. Or if x is a true-false kind of variable, it'll just be written as like probability of x. And capital X will often refer to the entire distribution of x. So beware that you may see these different things, and that it matters whether it's a capital X or a lowercase x. Okay? If it's an uppercase x without a value, that usually means the probability distribution of the variable x. Okay? So conditional probability, let's just say a word about that. So we're doing AI, and the whole point of AI is to do cool, fancy information processing and taking advantage of information you know to derive inferences and stuff like that. So if this is the universe and this is the set of states in which P holds, in which P is true. So these are the ones where P, well, let's say, how about X equals true. And then up here are the worlds where X equals false. Then, let's see. How about that? Okay, these are the worlds where Y equals true. Y equals true, if I can draw the letter Y. And here are the ones where Y equals false. So the probability of Y being true, if you get a random world, is 0.5. It's true in half the worlds. But if we know that X is false, that information dramatically skews our feelings about Y. Right? The probability of a random UNH class being fun. But then if you know that it's taught by me, it radically skews your view. So this is called conditional probability. So conditioned on previous information that you might have. So the probability of Y given X is the probability of Y and X divided by the probability of X. Y. No, wait, it does matter. This is incredibly important. Oh, yeah, it is Y. Ooh, that's embarrassing.
You just swapped the variables.
Well, no, this is actually super duper important. So X and Y is the probability of Y times the probability of X given Y. Yeah, I think that this is not right because this is right. And this would lead me to believe that X given Y is going to be X and Y. So this should have been X. Yeah. 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 So does everyone see why this is actually one of those things that's actually pretty intuitive? So, we're interested in this. If we're interested in the probability of Y being true, given that we know that X is false, we should have made this the X be true part. Can we do that? Am I still allowed to do that? Can I just relabel this as being true and this being false? So here we've got X and this little triangle at the very top is where we have X and Y both being true, and this whole rectangle is where we have X being true. If we want to know the conditional probability of Y being true, given that we already know we're in this upper rectangle, then it's the area of this over the area of the whole rectangle. Right? So that's pretty straightforwardly the probability of Y given X is the probability of X and Y over the probability of X. Yeah, okay. So does everyone understand that conditional probability? This little bar is given. Y given X. All right. We know something. We know X, and now we're wondering about Y. Okay. Any questions? Adam.
So are the notes wrong?
Oh.
You just swap Y and X. It's Y given X. So X is Y.
I would be really bummed if the notes were wrong, but it wouldn't be the first time. Yeah, I think the notes are fine. Yeah, the notes have this case up here where we're talking about x given y. Then you divide this by y. Here, if we're wondering y given x, we divide by x. Okay? So this you really have to understand. There's going to be something coming up in about a month called Bayes' law, and I can never remember it, but as long as you know this, you can derive it for yourself in about 5 seconds. So you want to make sure you know this.